very much for the invitation. So today I'm going to talk about dynamical degrees of self-maps on abelian varieties. So first of all, I will give you some background about what are dynamical degrees and this and the motivation of my question. So there are two sides. So one is from complex dynamics, and another one is from number theory. And then I will describe my results and some other results from other people. And in the end, I will list some questions. Okay, so first of all, what are dynamical degrees? So suppose we are giving a arbitrary topological dynamical system. So in other words, X is a compact metric space, and F is a continuous self-map. And then there is almost the most fundamental invariance associated with this system, so-called topological entropy, denoted by H top of F. So this is a non-negative real number, so which is used to measure the rate of divergence of the orbits of points. So roughly speaking, that's the complexity of this system. So the definition due to Bowen and Lindbergh is quite analytic. So I will give you a definition here. So X is a compact metric space, D denotes the metric, F is a continuous self-map. Then for any given large number n and some real number, positive real number epsilon. So 2 points x1, x2 are called in epsilon separate if their distance is greater or equal to epsilon. The distance is defined by in this way. So d is the original distance, and then we define a new distance dn. So using the maximum of the orbit, and then the topology entropy of this f is defined by these two limits. So first, we take the logarithm of capital N of n epsilon, so which means the maximum cardinality of n epsilon separate set. So which is a finite set. So this guy is a finite number because X is a compact space, and then log capital N divided by N, take the limit sup, then take the limit of epsilon. So this is so-called topology entropy, which is quite analytic involved. But the point when our X, if our X is a compact color manifold of dimension n. So for example, a smooth complex project variety X in some the ambient space, the project space, P to the capital N, and F is a holomorphic self-map. Then it turns out that the topology entropy is equal to the logarithm of the maximum of all eigenvalues of the induced pullback action on coherent ring. So here F, this star means the pullback, and the H star is the total coherent ring. Because for this coherent ring, for example, we can choose the Dirac cohomology or Betti cohomology, it doesn't matter. So we have the following Hodge decomposition. So for example, H to the I is equal to the direct sum of HPQ. So P plus Q is I. And then this eigenvalue, so lambda is the eigenvalue of this linear transformation. And then we don't have to consider all eigenvalues. So it's enough to consider eigenvalues of this, the pullback action on HKK. So the maximum of this, all of this absolute value of lambda equal to the maximum of this maximum. Okay, so this maximum is our dynamic degree. So this is the dynamic degree of the KIAS dynamic degree of this F. So it means that the topological entropy is equal to the logarithm of the maximum of dynamic degree. Okay, so now I give you the definition of case dynamic degree. In this setting, X is a compact Cayley manifold, F is a holomorphic self-map, then the case dynamic degree divided by dk is this guy is just the spectral radiance of this F star HKK. So it's the maximum of epsilon value of eigenvalues. So then we also call this the maximum of all log dk, call this one algebraic entropy. And then the algebraic entropy equal to the topological entropy by Gromov and Euromedian theorem. So for F is a holomorphic self-map, and X again is a compact Cayley manifold. Okay, so this is the motivation for studying dynamic degrees. So dynamic degree is related to the topological entropy. So in some sense, the dynamic degrees can also be used to describe the complexity of this system. So the topological entropy is equal to the algebraic entropy, and the algebraic entropy is defined by dynamic degrees. Okay, so any question?
So your F here is only required to be holomorphic self-map, no need to be surjective or dominant, right?
It doesn't matter. So if this guy is, you just need to replace the image by, right? You can replace X by its image.
Holomorphic is important. Yes. Meromorphic
yes,
is
yes.
okay.
Right, correct. So the point is this F has to be holomorphic. Otherwise we only have the one direction.
May I ask a question?
Yeah, sure.
Can you go back to the topological entropy? So here the capital N denote the maximum cardinality of an n-dimensional separated set. Why do you take the maximum cardinality of? So this is definition, right? Dn x1 x2.
Yes, this is definition.
And why do you take the maximum n epsilon separated set? But do you choose one epsilon separated set or the maximum cardinality? What does it mean? Maximum.
Because so for fixed n and epsilon, right.
Okay, I understand. Okay.
Yeah. Okay. So actually, we will not go back to this definition in this talk. So we only focus on the algebraic one. So for example, this algebraic entropy. Okay. All right. Okay. So now, previously we are talking about the dynamic degrees of a holomorphic self-map, and the definition is given by the spectral radiance of the pullback action. So now we talk about the dominant meromorphic self-map, but in this case, the spectral radiance doesn't work, so we cannot use the spectral radiance to define dynamic degree because the pullback action is not functorial. So the composition of two maps is not preserved by the pullback. So the dynamic degree can be defined in this way. So we use the intersection numbers. So we choose the arbitrary Kähler form from this Kähler manifold. So divided by omega x. So we consider this number. So f to the m, then pull back omega x to the k, and then times omega x to the n minus k, and then we get some number because this is the top form axial of dimension n. And then we consider the limit of mth root of this intersection number. Or we can use the matrix norm. So these two are equivalent. So we can also use the matrix norm. So we give arbitrary norm for this complex vector space, and then we have an induced norm for this linear transformation. And the norm doesn't matter because we take the mth root, and then the limit of this mth root. Okay, so now we actually have 3 definitions for dynamic degrees of a homomorphic map of complex manifold. So these 2 define for more general for dominant meromorphic self-map. But if F is homomorphic, we have 3 definitions. These 3 are equivalent. So this guy is the eigenvalue, the square radiance of this linear transformation. And these 2 defined by one by insertion number, one by the matrix norm. And the last 2, these two are actually independent of the characteristic of the ground field. So for example, here we don't need X to be a Kähler manifold. So you can replace X by any arbitrary smooth, for example, smooth project variety defined over arbitrary field. Then we also we choose arbitrary polarization. We choose ample divisor. So replace omega X by HX and consider similar initiation numbers. And also we can replace the coharmonic group by eta coharmonic group. And then we give this vector space a norm, then we consider induced norm. So these 2 definitions are characteristics free. So now we can talk about the more general version of dynamic degrees. So dynamic degrees in arbitrary characteristic. So let X be a smooth project variety of dimension n. We choose an arbitrary ample divisor HX, and let F be a dominant rational self-map. So we assume everything is defined over algebraic closed field K of arbitrary characteristic. So we have 2 ways to define the dynamic degrees. So one again, so the first one we use the initial number. The second one is the limit of these norms of this linear transformation. We choose arbitrary Wei coharmonic group, but in general we choose eta coharmonic group. So we have this linear transformation. We fix the norm on this vector space, then consider the induced norm. Okay. So the first one is defined by the initial number, but this guy is also equal to this pullback action. So the f to the m pullback of this nk of x. So here is n to the k. This stands for the finite dimensional real vector space of algebraic cycles of codimension k on x modulo the numerical equivalence. So we consider algebraic cycles or real coefficients. So these are finite dimensional real vector space. And this Wei coharmonic group is usually taken to be the eta coharmonic group. So with the QL coefficients. So here L is a prime number different from the characteristic of our base field K. So we have 2 definitions for this dynamic degree. So I did the lambda K. I use the lambda K to deliver the first one, and the chi2K to deliver the second one. And then the question is for any K, I call this chi2K the cohomological dynamic degree. So is this chi2KF the same as a numerical dynamic degree lambda K? Okay, so this is a trans question in 2016. So if K, our base field K is C, so if then the 2 are the same. So as I said before, all 3 are equivalent. So actually these 2 are equivalent because it's not hard to prove the 2 are equivalent. So but we just use some a little bit Hodge theorem and some linear algebra. So for example, this limit the limit of this mth root of this initial number, this guy is equal to the limit of mth root of this norm, the norm of this linear transformation. The propagation restrict to HKK. So these two are the same just by linear algebra. So you fix a norm on this guy. So if you choose a norm on this guy, it is not too hard to prove it too. Okay, so and then these two are the same. This is due to Dean, I think. So Dean proved this one in 2004, I think. So in other words, all other components of HPQ with P not equal to Q, so are bounded above by HKK, by the norm of this linear transformation.
May I ask a question?
Yeah, sure.
So previous page, can you define the number of cycles over C also? The number?
Yeah, sure. You can define this one. You can replace R by C. So this doesn't matter because this R n to the k of x. So this one is so first of all, this one is a finite generator abelian group.
Yeah. So
it's defined over Z. It's a Z module.
It's not finite number, right?
No. This n to the k of x is a finite generator abelian group.
So and then what's the absolute value? Is number? No. What's the absolute value?
No, this is not absolute value. So this guy is this guy tensor with R is a backspace. Then we consider
this is the number of the dimension. I see. This is the dimension of the vector space.
This is the functor. This is the functor, so it's considered small.
It's a linear transformation.
And then the absolute value is the dimension or
maximal coefficient of the matrix. You can take the maximal absolute value of the coefficient of the n times n matrix. Yeah, I guess.
If F is holomorphic, if F is holomorphic, then this guy is just the spiradians.
It's the matrix and then the norm of the matrix.
Yes, the norm of matrix.
Norm of the matrix. Okay. FM star is metric and the map, right? Okay. Thank you.
Yeah. Okay.
Well, may I ask one more question? That naive question. If F is a Frobenius map, then what is this value?
Yeah, this is my next slides will tell you.
Okay. Thank you.
The next slide is after this one. Okay. So our question is really about the positive characteristic. All right. So before we talk about Frobenius, so here's a easy inequality. So we have the following diagram, so which is preserved by the pullback map. So we have this is a chart group of so this is the group of algebraic cycles of quadrant K modulo the rational equivalence. So this is a chart group, and then this if we quotient this one by the homological equivalence and tensor with QL, we have an injection to the common group because we modulo the homological equivalence. So this is an injection. We quotient by torsion. And on the other hand, we have this suggestion. So the chart group modulo the numerical equivalence because the homological equivalence is finer than the numerical equivalence. Then we have this suggestion. So this suggestion is n to the k tensor with QL. Okay, but it doesn't matter with tensor with QL, tensor with R, or tensor with C because everything is defined over Z. So this guy is defined with Z. Okay, using this map, we can easily see that the lambda k of F is less than or equal to chi 2k of F. So chi 2k is given by either here. So the chi 2k is from the propagation of F on H2k, and the lambda k is from here. So lambda k is bounded above by chi 2k. Okay. So here is a remark. The standard conjecture D predicts that this vertical suggestion is actually a isomorphism, but we don't need that, right? So because this guy dominates this guy, but this guy is we can embed it onto H2K. So we have lambda K less than or equal to 2K. So hey, this is the easy inequality. So this question now turns out to be if chi to k is less than or equal to lambda k. So the other way. Okay. Now, so now we are going to talk about the forbidden map. So this is another evidence from lemma theory. So why should we believe this inequality? So we have the following evidence noticed by Tron from lemma theory. So suppose x0 is a smooth project variety defined over some finite field fq, and we let x be the best change of x0 to the algebraic closure fq bar, and let this f be the forbidden endomorphism of x with respect to fq, the defining field. And then the Grothendieck Lefschetz trace formula. Using this formula, we can express the number of fq to the n points of x0 in terms of the traces of the propagation of f to the n on a Taubman group h to the I. Okay, and then the way we have this so-called Weiss-Riemann hypothesis and proved by Delin in 1974. So the characteristic polynomial, so I denote by p sub I, pi of t, the determinant of this linear transformation f is the forbidden. So f star action on this h to the I. So the characteristic polynomial has only integer coefficients independent of L, and the eigenvalues of this one, the eigenvalue of this f star on hi are algebraic integers of absolute value q to the half I. So all eigenvalues have the same absolute value, so q to the half I. So they are algebraic integers. Okay, so I think this answers your question, right? So if f is a forbidden, so then this chi I is equal to q to the half I, and then chi 2k is equal to q to the k, right? So on the other hand, it's easy to see that lambda k is defined by defined on the numerical group n to the k. So lambda k of f is equal to q to the k. So in fact, more generally, we have lambda k of f is equal to q to the k for any polarized endomorphism. So polarized endomorphism means that f the product of hx is a fixed ample divisor. The product for hx is a linear equivalent to some multiple of hx. So this is true for any polarized endomorphism. And the forbidden is a special polarized endomorphism. So for forbidden, we also have lambda k of f is equal to q to the k. Okay, so now you see that for forbidden, we have this equality. So lambda k of f is equal to chi 2k of f. Both of them are q to the k. So this guy lambda k equal to qk is easy, but this guy is very hard. So it's actually a Weiss-Riemann hypothesis, or is a consequence from the Weiss-Riemann hypothesis. But later we'll see that they're equivalent. So Tron's question has a positive answer if f is a forbidden endomorphism, capital F. Okay, so here's another conjectural evidence. So for this conjectural evidence, it means that it says that if we assume standard conjectures by Bombero and Grothendieck, So in particular, we assume standard conjecture of Lefschetz type and of Hodge type. And then CS argument on carrying version of Weiss conjecture with Lehman hypothesis. So it works verbatim in positive characteristics for any polarized nomorphism. And actually, these two conjectures are proposed to generalize CS argument to positive characteristics. So CS argument is for compact Cantor manifold. So it works only over C. And then if you assume these two conjectures, then it works for any arbitrary positive characteristic field. But we don't know the two conjectures so far. So conjecturally, chi of F is equal to Q to the half I for any polarized nomorphism. And again, for the other side is easy. So lambda K of F is Q to the K. Okay, so here's a remark. So in fact, we need a standard conjecture of Hodge type for the product variety. So if we want to show this lambda I of F is equal to Q to the half I for polarized nomorphism F on X, so we need this conjecture for X cross X. Okay, but even for surfaces, this X cross X is has dimension 4. So we don't know the Hodge type conjecture for this dimension 4 variety. So in other words, this argument hasn't been completely worked out even for surfaces. But we know we know before Daniel gave the proof with Lehman hypothesis, the general proof, he proved with Lehman hypothesis for K3 surface first. So his proof relies on using another argument, so relies on this called Kuga-Satak construction.
Sorry for interruption. So for you said the standard conjecture of Hodge type. Do you mean the well-known Hodge conjecture for X?
No, they are different. No, they are different. The well-known Hodge conjecture is for compact Cantor manifold. Is about no, they are different. This Hodge type, this standard conjecture of Hodge type is something like index type. The Hodge index theorem.
Okay.
Yeah. So for if X is surface, we know the Hodge. If X is surface, we know the standard conjecture of Hodge type. It's just the Hodge index theorem.
You mean the Hodge index theorem in characteristic P is not known, right? Or what?
Yeah. But it's true for surface.
Okay. And also you say that in the fifth line, chi I F equals to Q to the power I over 2. It is only known for Frobenius, right?
Oh, you mean this guy?
No. Just the current. Yeah. Here. The fifth line. The fifth line.
Okay.
This is only known for Frobenius by Deligny, right? For polarized, yes. It is not known.
Yes. So if F is a capital F, the Frobenius, then this is proved.
But even for polarized, it is not known.
If it's for polarized, it's not known.
Okay.
If it's for polarized nomorphism of a surface, I don't know.
Surface, I guess it is true because okay, we will talk about later. Okay.
Yeah. So I don't think the polarized nomorphism of a surface, this is true. Maybe you know more, right? I don't know. Okay, so now the interesting part is actually Truong's conjecture can imply this Weiss-Lehman hypothesis. Okay, so recall this F is Frobenius, and the Weiss-Lehman hypothesis says that all eigenvalues of this linear transformation have absolute value Q to the half I. So if we want to prove this statement, so we have the following two standard reductions. So first of all, we can use the Poincare duality. We just need to prove chi I of F is at most q to the half I. So if chi I of f is at most q to the half I, then all eigenvalues have absolute value less than equal to q to the half I. By comparing duality, then you can get the other direction. So all eigenvalues is greater than equal to q to the half I, then they are equal. And then another reduction, we can use this so-called product trick. Then we just need to show chi 2k of f is at most q to the k. We don't have to show all chi I for all I. We just need to show chi 2k for even indices using the product trick. So we consider x cross x, and for a Bayes map on x cross x, then it's easy to show. We just need to show chi 2k. Okay, so now if we assume trans-conjecture holds true for Bayes, then chi 2k of f is equal to q to the k. Then you see we have this inequality, then we have this inequality, then we get this statement. Okay, and this is a remark. So it because trans-conjecture inverts with limit hypothesis, so it makes sense to give a lamb like a dynamical with limit hypothesis, something like that. Okay, so before I talk about the result part, is there any questions?
Okay, let me ask you a question. You know a paper by Helen Eno and Srinivas. They did a dimension 2 case, so right? They proved.
Yeah, I know. Yeah, I know Eno and Srinivas paper. So which is here?
Oh, you said already? Not yet.
This is the result and proof. So the first result is Eno and Srinivas result, not my result.
Oh, so this answer the same Munsell equation, is it?
Oh, no. You see here? So in their case, so F is automorphism.
I see. Okay, I see. Okay, all right. Thanks. Yeah.
Yeah.
Excuse me.
Yeah.
May I ask? So previous page. So one more previous page. Yeah. So here this is over C, right?
Oh no.
Kähler version of is over C.
Kähler version is over C, right?
This is over complex.
Yeah, this is over complex number. So C I proved that if F is a polarized endomorphism of a complex Kähler manifold, yeah, then we have this one.
Okay, thank you.
Oh, actually, we actually have all eigenvalues of have absolute value q to the half I.
Okay, thank you.
Okay, so the first result is due to Eno and Srinivas 7 years ago. So they proved the first consider the surface case. So F is the automorphism of a smooth project surface defined over a finite field. And then they show that the maximum of absolute values of eigenvalues with this propagation on H star, so the total coordinate ring, because dimension of X is 2, we have H0, 1, 2, 3, 4. So the maximum of eigenvalues is achieved on this QL span of this polarization, or the polarization span of f to the n of hx for any integer n. So the span of this guy is smaller than, so in some sense, this is all comes from the ample divisor. So in H2, but this guy is contained in the Lorentz group. The Lorentz group contains all algebraic cycles, but this one just contains f to the n of hx. But that shows that this is enough. This is enough to get the maximum of absolute values. So in particular, chi2 of f is equal to lambda 1 of f. but lambda 1f is greater than this one. So therefore chi2 equal this one. Okay, so actually they proved even more. So they proved the pullback action on the transcendental part of H2 is of a finite order. And this is true over complex numbers by the Hodgkin theorem, because the transcendental part, so outside the transcendental part, we have the algebraic part by the Hodgkin index here, which has an index of 1, the hyperbolic index, so 1 of positive 1 and the negative, the rest is negative. And then if you consider transcendental part, all are positive, so is you will get a finite group. So that proved this is also true of any finite field. But they only consider F with the automorphism. So the proof of their proof depends on the classification of surfaces. So the most difficult part, I think, is K3 surfaces. So for K3 surfaces, they use K3 surface and abelian surface. So for K3 surface, they use some results related to Taylor conjecture. So it's not easy to get their result. And for abelian surface, they also use the Taylor conjecture. So I think their proof is not trivial. Okay, and then here's another result of Tron. So he proved the equivalence of entropy. So we may call this the maximum of all chi, call this one the atoll entropy of F, and the maximum of all lambda k, the algebraic entropy. So he proved these two entropy coincides. Although we don't know if individually we know this chi2k equals lambda k, but the maximum are the same. Okay, so in particular for automorphism of surfaces, which has been considered by Eno and Srinivas, the lambda 1 of F is equal to lambda 2 of F, because F is automorphism, so both of them are 1. And then the maximum of lambda k part is lambda 1. And the left side, now we know the chi2 of F is less than or equal to maximum of chi is equal to lambda 1. So chi2 is less than or equal to lambda 1, but we know the other direction. So we know chi2 is equal to lambda 1. So for automorphism of surfaces. So we don't need the Taylor conjecture for K3 surface and the abelian surfaces. Okay, so now here is my result. So I proved this this equalities for abelian varieties. So abelian varieties are high-dimensional analogs of AB curves. So over C, they are compensatory, like C to the G divided by some lattice. So in positive characteristics, so they are complete connected group varieties. And in particular, they are projective, they are abelian group varieties. So we don't need to consider F is a rational self map, because for abelian variety, all rational self maps are actually self-morphism. So we just need to consider a surjective self-morphism of abelian variety. Okay, so this in particular answers a question of Eno raised in American Institute mathematical workshop. This question. So if A is abelian variety defined with some finite field, so U is a fixed automorphism, and then U induces this pullback action on total commutative group, eta commutative ring, and then let alpha I be eigenvalues. That this is the absolute value of alpha I. And then take a subring in this H star, the total common ring generated by polarization, stabilized by U. So this is just the same as their theorem in surface case. You choose a ample divisor HX, then we consider the subring generated by this ample divisor, stabilized by U. So we have U to the n of HX and the HX square and HX to the n in this H star, the total common ring. Then this subring, consider this subring, then the maximum Archimedean size of the eigenvalues of a subring equal to the maximum Archimedean size of the eigenvalues of the total common ring. So if A is 2 is okay by their result, that proves if X is, that proves the dimension 2 case, in particular for abelian surface. If K is C and A is a smooth probability, this is true, just by some Hodge theorem and linear algebra. Okay, so so far, is there any question before I go to the idea of the proof?
Just one question. So the proof of Chong is independent of the proof of Ano and Srinivas. They don't use theta conjecture or something.
Yeah, right. So his proof is doesn't rely on. So he give us his proof. So his result recovers the Ano's result. For example, recover this part.
Okay.
One small question. You see the Ano, Srinivas, and also Chong, they always require the base field to be FQ or FQ bar. Is it very important?
So actually, this is not that important because we always have for this lambda k for this invariant, they are we can deform them. So when you deform them, you have some inequality, but that inequality is good for us. So we don't need to care about the base field.
You mean you can always reduce the problem to over FQ bar or FQ?
Yes, yeah. Yeah, that's true. Okay, so now we assume this F. So for simplicity, we assume F is just a group endomorphism. So there is no translate. The translate part is trivial. So we denote the characteristic polynomial of F by P log F of T. So this is a characteristic polynomial of F star on H1. The H1, the first eta common group of X. So which has only integer coefficients and degree 2g. G is the dimension of X. So here F is an endomorphism. So it's the actual endomorphism. Then the characteristic polynomial has only integer coefficients. Later we will consider, we can generalize one to the endomorphism Q algebra. So with Q coefficients. So we can consider some give this F some Q coefficient. Then the characteristic polynomial has the rational coefficients. So we will use Q coefficient later for Rosati evolutions. Anyway, so we denote all complex roots of this PF of T by pi 1, pi 2, pi 2g. So we have 2g complex roots. We denote them by in this way. Maybe they may have some multiplicities. So over C, it is well known that the 2g complex numbers fall into G pairs with each one consisting of 2 conjugate complex numbers. Because over C, we have the Hodge decomposition of this H1. We can this H1 is isomorphic to H10 and the sum of H10 and the H01. So for each root, we have its conjugate, complex conjugate. So we have G pairs. So first, so we can show that this is also the case in positive characteristic, although we don't have the complex conjugate. So I show this one, use the classification of endomorphic Q algebras. We use endo up 0 to denote the endomorphic Q algebras. So we have the classification of the normal Q algebras says that this guy is a semi-simple Q algebra. When you tensor with the R, say, then it is isomorphic to some matrix algebra. Then we can show that in that case, for each one we have for each root we have its complex conjugate. Okay, so suppose this is true, then we may write 2G roots in this way: pi 1, pi 2, pi G, and they are conjugates: pi 1 bar, pi 2 bar, pi G bar. So we can assume they have been sorted in this way: the absolute value of pi i's in decreasing way. So now, since for abelian varieties, the eta complement group is very good. So H2K is equal to the wedge product of H1 to the 2K. So this is the same as the complex abelian variety. So this is also true for eta complement group. And then, so if we know the action on the proper action of F on H1, and the H2K is equal to the wedge product of 2K, then we know chi2K of F is nothing but the product of pi I to pi I square, the square of absolute value of pi I. So chi2K of F is the maximum of absolute values of eigenvalues. So we know eigenvalues are here, so the maximum must be this one. All right. So we call this we choose this polynomial. So we choose the first G, this pi 1, pi 2 up to pi G. We take these G eigenvalues, then consider this polynomial. So this polynomial has C coefficients, Albert polynomial divided by P F super A of T. So this polynomial satisfies this property. The characteristic polynomial of F is equal to this Albert polynomial and its complex conjugate, because the roots are in this way. So in some sense, this Albert polynomial is a positive characteristic counterpart of the analytical representation of this map in character 0. So if X is a complex abelian variety, then we have two representations of this F. One called analytical representation, and another one is a rational representation. So consider the induced map of this F on the universal cover and also on the lattice. So we have two representations, and this guy corresponds to the analytical representation. So this one corresponds to the original one, the rational representation. All right. So because we have law in chi2k of F is equal to this number, so we just need to show that lambda k of F is also equal to that number. So recall that lambda k of F is equal to, by definition, equal to the limit of this mth root of this initial number. So now we let this F, so F deck, we use this one to denote the Rosati evolution of F. So because we have this ample divided Hx, we use this ample divided Hx to give this X polarization. So phi is a map from X to X hat, which is a dual abelian variety of X. So pick a 0 of X. So this phi is correspond to this ample divisor, and then this F, the Rosati evolution is Rosati evolution is in endo 0 of F. So it is in general it's not an homomorphism, but it's in the homomorphism Q algebra, because we need to take some inverse here. So we have some coefficients. So we map phi to x hat, then we consider the dual map, so from h hat to h hat, then we maps back to x. Okay, and then here is a lemma. The lemma says that the arbiter polynomial of this f that composed with f is unique and has only rational coefficients. So a priori, the arbiter polynomial has only complex coefficients. So this guy has only rational coefficients. So moreover, if we write this polynomial in this way, and then the coefficient equal to g to the k, and this initial number divided by the top self product of hx.
Sorry for the interruption. So what do you mean by unique?
Yeah, so this is a good question. So you see here, we define arbiter polynomial in this way. So t minus pi I, but you can switch pi I with pi I bar, right? So the rule of pi I and pi I bar are not canonical. You can switch pi I with pi I bar. So here, you can choose pi 1 and pi 2. You can also choose pi 1, pi 2 bar.
Okay, I see.
Yeah, so it means that this arbiter polynomial is not unique. You will have a lot of arbiter polynomials for arbitrary f. But in characteristic 0, we have a canonical polynomial. So we can decompose this the characteristic polynomial of f as the characteristic polynomial of analytical representation. But in positive characteristic, I don't know. So I can just choose one of them. So for each one, you choose one of them, then you will have a lot of 2 to the g choices, maybe. So, but this guy is symmetric. You see that this one is symmetric. Then because this one is symmetric, then we can show that this one is unique because it can be written down in this way. So it must be unique. Okay. Okay, so the coefficient up to some sign is equal to, and also up to some constant g to the k divided by hx to the g, so equal to this one. Now you see that this one is quite close to the definition of lambda k. Lambda k equal to, in the definition of lambda k, we have this initial number f to the m pullback of hx times hx to the dimension of x minus k. So then we just need to replace this f by f to the m, right? So we consider the f to the m, the resulting evolution of f to the m composed with f to the m. And then right hand side, we have the coefficient. Okay. Now here is a factor about the endomorphism Q algebra. So as I mentioned a little bit before, this endomorphism Q algebra is a semi-simple Q algebra. So if it turns we are, it's isomorphism product of copies of those matrix algebra with either R coefficient, C coefficient, or quaternion coefficient. So moreover, we can fix isomorphism so that it carries the resulting evolution into the standard evolution. So the standard evolution is in this matrix algebra. So for example, for this one, we just map matrix to its conjugate. For this one, is complex conjugate. For this one is a quaternionic conjugate. But we can even further embedding quaternionic matrices into complex matrices. So we map the embedding so the R dimension quaternion matrix into 2R dimension C complex matrices. And then this F, our original endomorphism F, will correspond to a complex matrix A log F. Then the resulting evolution corresponds to the complex conjugate. and f to the m is a power matrix af to the n. The resulting evolution of f to the m is a conjugate of this power matrix. And the roots of this orthogonal polynomial are the same as the eigenvalues of Hermitian matrix. So this one, so this map f to the m that composed of fm correspond to this Hermitian map. So the roots of this orthogonal polynomial are the same as this eigenvalue. So the eigenvalue of this Hermitian matrix is just the squares of singular values of the af to the m. Okay, so now we can apply the lemma 1 to f to the m. So we replace f by f to the m. The left hand side we have this one, and the right hand side, so we can go to lemma 1. So we replace f by f to the m. So left hand side, we can expand this one as a product of t minus roots of this polynomial. And right hand side we have this one. So we have the correct initial number to define lambda k. So the roots of this polynomial is a singular value, so sigma 1, sigma 2, sigma g, and then this ek is the elementary symmetric polynomial of
Sorry.
Yes.
So, for interruption. What is singular value of a matrix?
Oh, yeah, this is by definition. So we have this arbitrary matrix. So this matrix may not be symmetric.
Mm-hmm.
Or may not be this is complex matrix, so it may not be Hermitian. But this one is Hermitian matrix. So the singular value of arbitrary complex matrix is by definition is the square root of the eigenvalues of this Hermitian matrix.
Oh, okay, I see.
So the eigenvalue of this Hermitian is the squares of.
Okay.
Yeah.
I didn't know the words. Sorry, thanks.
Because this one Hermitian matrix, so eigenvalues are all non-negative.
Yeah. All right.
Yeah. So the roots of this polynomial are those singular values. So sigma I f to the m. Then the coefficient could be written using elementary symmetric polynomial of those roots. All right. So now we just need to do some calculation. So lambda k of f by definition by the two. So this is the definition of lambda k, and then by 2.5, then is the limit of mth root of this elementary symmetric polynomial of those g singular values, square of g singular values. And then this guy is equal to the maximum of all I1, I2, Ik, all possible choices of the limit of the product of those limits. This is basic. I think this is just using some basic analysis. So the limit of those sums. So because this is elementary symmetric polynomial, so it's the sum of those monomials. And then the limit, when you take the mth root, then it is equal to the all maximum of all products. And then now the point is the limit of those singular values, the limit of the limit of those singular value to the 2 over m goes to the square of eigenvalues. So this is by the lemma 2. I will show you this one in the next slide. And then now it's easy to see because we have this guy, pi 1 is the maximum, pi 2 is the second maximum. Then the maximum of all those products must be pi 1, pi 2, pi k to square. So this one is our 2k. Okay, and then now the only thing is these singular values, when we take the mth root, it goes to the eigenvalues. So this by the second, this lemma 2, this is just a linear algebra. So if A is an arbitrary complex matrix, Then denote the eigenvalue by pi 1, pi 2, pi n. We list them in this way. And then we let sigma 1, sigma 2, sigma n. This one, the singular values of e to the n. And then we have this limit. The limit of mth root of sigma I of e to the n is equal to pi I. Because in general, for a matrix, the singular value is not the same as the eigenvalue. If A is symmetric, then it's okay. But if A is arbitrary, then sigma I is not equal to pi I, so we don't have this, we don't know if they are same. But if when we take the mth root, it's the same. So this lemma is just give you some asymptotic behavior of roots of singular values. Okay, so in the last slide, so I'll give some questions. So the first question, so this question has been asked before, I think. So what about the arbitrary endomorphism of or rational self-map of a surface? So in particular, the most intricate case might be the polarized endomorphism of K3 surfaces. So if this map is automorphism, then we know this is true by a no and three inverse result. So what about the arbitrary endomorphism? And actually, there is another question. What about the arbitrary correspondence of abelian variety? So for abelian variety, arbitrary endomorphism is okay. So, but what about arbitrary correspondence? So correspondence is more general than rational map. And we can rephrase everything in terms of correspondence. And actually, trunk conjecture is about, original question is about correspondence. And the last question, so is there a motivated interpretation for this question? I think I will stop here. Thank you.
Okay, thank you very much. Okay, any questions? Maybe you can. Okay, maybe you can go back to the previous slides, then people can ask.
Yeah. Can I ask a question?
Yeah.
So as for question one, are there interesting class of polarized endomorphism on K3 surfaces? Is it like Frobenius other than Frobenius?
You mean more concrete?
So in characteristic 0, there are no polarized endomorphism on K3 surface, right? So what is the interesting class of polarized endomorphism?
Yeah, so it will be interesting to prove that there is no, so for example, any surjective endomorphism of K3 surface is actually automorphism, except Frobenius in character P.
Oh, okay.
I guess you mean Frobenius means there are several Frobenius. You mean geometric Frobenius or all the Frobenius?
Yeah, except that one.
What happens if it is only a purely, for example, a Frobenius composite with non-identity automorphism? Then it is not a Frobenius. You see, not the usual Frobenius.
Yeah.
So I guess.
Yeah,
right. Okay. And one more question. What do you mean by motivic interpretation?
Oh yeah. So because for example for this question, so if you consider K3 surface, you really have to show that the induced action of the morphism on the transcendental part can be bounded in some sense by the induced action on the algebraic part. But the transcendental part is quite, so we don't know too much about the transcendental part. but there is one way to consider the transitional part. So if you consider the motif of this K3 surface, so we have the Kronos decomposition for K3 surface. We can decompose the H2 part as H2 edge and H2 transcendental part. So the transcendental part corresponds to the algebraic cycles of degree 0.
Mm-hmm.
Algebraic 0 cycles of degree 0.
Mm-hmm.
Yeah. So in this way, I can see that there is also, this is also algebraic, because this T2 part, this transcendental part is so-called the Algebraic kernel. So it's the algebraic cycles of degree 0 modular rational equivalence.
Mm-hmm.
So I want to know what's the induced action of this map on this group. I don't even know how to define the invariant associated with this action, because this one is not. So there is something about the finite dimensionality of this motif. I don't know. So I don't know how to define an invariant. So this is why this is called motivic interpretation. Can we so define everything using define similar invariant lambda k something like that using a motif theorem?
I see. Yeah.
Okay, I have a question. So for abelian varieties, you prove that lambda k equals to lambda k equals chi 2k, right? And can you show that for Searle's theorem in positive characteristic case that eigenvalues are all q to the power I over 2, k over 2, or k over 2? For polarized, I mean, endomorphism.
So for polarized endomorphism of abelian variety, do you mean that?
I mean lambda k, not lambda k, all the eigenvalues, the pullback action on the HK has absolute value q to the power I over 2.
Yeah, that's true. That's true.
That's true, yeah.
You can either using this one to show that, or you can using with original argument.
You mean you only need to show the minimal ones are also the same. Means if you take you can see, because your lambda k is the maximal one, and chi is
so lambda k maximum means that all eigenvalues.
Okay, so you consider the smallest one, and they are also the same.
No, you're using this one.
Okay.
You just need to prove all eigenvalues are less than or equal to q to the k, and then by congruity you have the other direction.
Okay. I see. Okay, any other questions? If no, let's thank the speaker. Okay, I'll give you applause. Okay, so then our next speaker next week will be Takio Shibata. Okay, maybe I'll end the talk and see you next week. Okay, goodbye.
See you.
Okay, see you. I'll go for lunch. Okay, bye.